So once again, welcome you all to the lecture series of digital signal processing. This topic is today's topic is on the frequency transformations in analog domain. Now we know from the last two classes, the last 2 to 3 classes, we understood how to obtain the transfer characteristics for a given specification. So either we will be having this kind of figure, or else we will be having this kind of frequency response. So where we use Butterworth approximation and we use for this Chebyshev approximation method. So once we have this is my output that I am supposed to get. So where I will be having some passband uh, frequency and passband attenuation, stop band frequency and stop band attenuation. So where this will be moving across the omega, and this is all about the frequency response curve. So for which we designed the filter response, so output. In order to get this, so we designed the filter response, and that filter response was h of s. So and this h of s was consisting of numerator and denominator. Denominator was poles and numerator is always 1, because both of them led to all pole model. All pole model. Now what is the next concept here? So this is all about design of filter. One thing, make sure that if you are trying to design a low pass frequency, now I want to transfer this to next frequency, stating that high pass filter. Now I have a some cutoff frequency. Okay, I will be designing for omega p1, let me assume, and later on I want to design this for high pass filter with another frequency omega p2, or I have a omega p1 cutoff frequency here, low pass filter, but later on time I start feeling that no, this should not be my cutoff frequency, I should increase little bit. So I come to the conclusion that this should be my omega p2. So you cannot start designing from the first, right? Only because of change in omega p1 to omega p2, you cannot start with first putting n value and taking log of based and all these. You cannot do it, right? So once again you need to do all this procedure and find out the value of n, then find out the poles, right? Sk value, then again go for h of s. So this becomes a very tedious job, only because of there is a change in the small frequency, that is cutoff frequency. You need to start designing from the first, means it is simply a very risky job, or very too much time consuming, right? So you in the industry you don't have much time to start with the once again initiate the system from the first, right? Because many times this will be trial and error basis, because sometimes what we do is we will be choosing that let me this be the cutoff frequency, so that I will be getting all the frequency component that is required, and later on time you feel that no, this is let me assume that this is somewhere else 2 radian per second is enough, and later you feel that no, let me increase it by 1 more radian per second, and then you start saying that no, let us design the filter for 3 radian per second. Now is it possible to start with the first? No, it takes a lot of time. So what we do, we have some transformation techniques, right? Again, I can transform a low pass existing filter to another low pass filter. So here let me assume this was cutoff frequency for designer for omega 1, and later on I want to design it for the omega p2. Or else I have a low pass filter, now let me design it for the high pass filter. Yes, it is also possible. Or I have a low pass filter, let me design it for the band pass filter, right? So why I'm trying to say is, so if you could able to design this low pass filter, right? So low pass filter. Now what is high pass filter is all about? So high pass filter is all about just shift in the frequency, just shift in the frequency, right? So which means that, so here you are trying to suppress these kind of frequency, higher frequencies are suppressed. So what do you mean by higher frequencies are suppressed? For these frequency I am putting zeros. I need this part of frequency, so I will be raising my poles, right? Now, what happens here? This is quite reverse, right? So from omega p1 up till omega p1, I want to allow. Later on, you decide that no, from omega p1 onwards, let me allow the frequencies. So what you need to do? Only need to do is put zeros here and put poles here, right? Raise your poles. So that's it. So that's a very simple technique that I adapt. Is it now? So in the and in such cases, if I want to have a band pass filter, that's again a very simple thing for me. So where I already have a low pass, I already have a band pass. Look at this. Now if I want to have this, so obviously this, if I want to have some particular frequency to be stopped, a particular frequency to be stopped, so this becomes narrow filter, band reject filter, right? Band reject filter. So right, so now where some part of filter are getting rejected, now what is to be done? So design one low pass filter, design one high pass filter, combine them, so that becomes band reject filter, right? So that's how, if you know to design basically a low pass filter and a high pass filter, if you just know the low pass filter, that's sufficient, because high pass filter is nothing but replacing your poles at zeros. So as simple as that. Now, if you want to design a band reject filter, like you already know poles, you already know how to design low pass filter, you already know how high pass filter. Just in between the filter that you want to reject, that is possible, right? So all about understanding about the thorough knowledge of the design of low pass filters. That's it. Now, with this, I have a small chart here. So where from that we will try to design. Fine. Now I have ready-made formulas for transforming the frequencies from one domain to another domain. So one domain to another domain means a low pass to high pass filter if I want to convert. So it is as good as design low pass filter, then convert it to any other filters in one sentence. Okay, design a low pass filter, design a low pass filter, convert it to any other filters, maybe it is for HPF, maybe it is for band pass filter, any filter. Only thing is you need to have a cutoff frequencies, that's it. Okay, now so these are the formula, uh, we can note down, or else uh, anyways these PPTs will be shared to you in the Google Class. If I want to design a low pass with a low pass filter, what does it mean? That's what I told you. I design a filter for one particular frequency, right? So let me assume that omega p1. Later in point of time, I want to have a different cutoff frequency. So I thought like, no, it should not be at omega p1. It is supposed to be lie at omega p2. Now this is my old frequency, and this is my new frequency required, right? So then anyways I have h of s that is already designed for this frequency, cutoff frequency. We will be having a h of s, right? So h of s means I will be having a standard form. In the denominator I will be having some polynomial equation. So in terms of this polynomial equation will be in terms of s, right? So now I need to replace this variable s by omega p divided by omega nu into s, right? So this is a small change that you are supposed to perform in your existing uh, transfer function, right? So that's it for converting low pass to low pass filter. Now similarly the same thing you are supposed to follow, that assume that you already have a low pass filter designed for omega p1. Now I want to design a high pass filter. From existing low pass filter I can transfer this to the omega p2, right, cutoff frequency. of omega p2, which means that from here I should start collecting my new frequency components. Now for which you will be having h of s for this, right? So you will be having h of s in the form of numerator to the denominator. In the denominator, this is a polynomial equation which consisting of s. Now replace s by this equation. That's it. So that is omega p. Omega p means existing or older one. In this case, omega p1. I replace this by omega p1. That's what the meaning. Okay. Into omega p new. So in this case, omega p2 is my new frequency, right? So divided by s. So this is a small transformation that you are supposed to adapt. Okay, so that you can change your low pass filter to high pass filter frequency characteristic curve. So that we call it as the frequency transformations in analog domain. Okay, where for LPF to BPF I just replace by S variable by this particular equation. So all these are derived equation. Directly we will be using the equation. Somewhere else you need to remember this. Okay, there is no other way. You have to remember this particular transformation that is going to be applied. Okay. Uh, Now, with this, immediately I'll go with solving example. I'll take one example from moving from LPF to LPF and one more example from LPF to HPF. That's it. Okay. Design Design a low-pass Butterworth filter of second order with passband edge frequency of 2 radian per second. Assume a omega p equal to 1 radian per second. So that's what. So I have, what is the meaning of this? So you already have a designer frequency for omega p that is equal to 1 radian per second. Okay, now you are supposed to design a new low pass filter where the cutoff frequency should be at this omega p should be at 2 radian per second. That's it. So that's what we call it as omega p new here. Now here one of the important point that what lies here. So Butterworth polynomials for different polynomials. Butterworth polynomials are ready-made polynomials will going to exist wherein for any frequency that you design, the transfer characteristic will be having some ready-made value in the denominator. So if it is single order filter, so which means h of s is a single order, then this will be of the form 1 by s plus 1. So this is n equal to 1 and this is my standard polynomial, right? This is my standard polynomial. Similarly, if h of s, if it is a second order filter, my h of s transfer function will be of the form I am telling about, of the form. Okay, so s square plus square root of 2s plus 1. This is a characteristic equation or a polynomial that we will be having. So I will be directly using this characteristic equation or a Butterworth polynomial as and when required for my formula, as and when required for my problem solving. So these are the standard polynomial we will be using to solve the examples. Okay, so if it is third order, then I have the equation. So most of the times in the question paper they will be giving you consider a Butterworth polynomial, third order Butterworth polynomial as this and as this for fourth order and fifth order as such. Okay, using this itself we try to solve for the uh, transformation of one analog form to another analog form. So here I will be considering. So let me write given in the problem what is the points are given. So omega p old frequency is given, that is at 1 radian per second, and omega p new. So I need to get the cutoff frequency at 2 radian per second. Okay, then I have a h of s polynomial. Since it is second order, okay, since it is second order, from the table I will follow this. Okay, we will be giving you in the examination, don't worry, but you need to understand that how to write this. So that is, so since it is a all pole model, so there will be no zeros in the numerator. So only thing is denominator consisting of the polynomial equation, that is in terms of s square plus square root of 2s plus 1. This is the standard form, right? So this is my standard form. Okay, now what I should do now, going back to the another table here. So look at this. If I'm moving from a low pass one type of filter, one frequency to another frequency, then I should replace my s by omega p divided by omega p nu into s. So that change I should do here, right? So let me perform that. So replace s with omega p divided by omega p of nu in, okay, uh, so here omega p, what is the old value of omega p? That is 1, right? So 1 divided by 2 is the new value. So this is to be replaced, that is s divided by 2 is supposed to be replaced in my equation 1. So let me call this as equation 1. Put s equal to uh, put x equal to s by 2 in equation 1. So putting this in equation 1, right? So h of s is equal to 1 divided by, so s is replaced by s by 2 whole square plus square root of 2 into s by 2 plus 1. So now if I solve this, I am going to get 1 by 4 times s square plus 2 divided by root 2, sorry, root 2 divided by 2, that I can write it as 1 by root 2, right? So this is can be written as root 2 into root 2. So root 2 and root 2 get cancels, so I directly write it as 1 by root 2 uh, s plus 1. So this is uh, the new h of s. So if you want to simplify, once again you can simplify that taking 4 as a LCM here. So if I take that 4 as a LCM, then again I'm going to get this equation as 4 divided by s square plus 2 root 2s plus 1. So for take s 4 as a SCM, and then finally you will going to get this as a new transfer function, that is new transfer function for what is the cutoff frequency here. So here the cutoff frequency is equal to 2 radian per second. That's it. So this is, earlier my frequency response was omega p was at 1 radian per second. Okay. Now I had an h of s for this. Okay. I replaced that h of s with this transfer curve. Okay. Now again look at this. This is a standard, that's why it is called as a standard form. Look, I have a s square, so polynomial remains same, s square, root 2 is also present, s is also present and constant. So again this only this value, which means that if you solve for this characteristic polynomial, you will going to get a different roots. When I say that different roots, so you have some roots for this, you have another roots for here. Roots are nothing but the poles. So when I am placing a poles in a different position, as compared to this equation, right? So I'm just altering my poles. I will be moving my poles. Let me assume that earlier my poles might be having at this position. After replacing, I may replace my poles somewhere else here. That's it. My entire equation will be according to these poles. That's the only change that I'm supposed to do here. Okay. So here this frequency is for 2 radian. Frequency curve is for 2 radian per second. That's it. Is this clear? So this is a very simple and straightforward, and only thing is you need to understand. So you need to know about how to write a transfer characteristic curve for a given h of s, and look at whether it is a low pass filter or high pass filter that you want to change it for. Okay, so one more example quickly we'll solve. So design a low pass Butterworth filter of second order. Sorry, this is not low pass, this is supposed to be high pass. Change this. Design a high pass Butterworth filter of second order with cutoff frequency. So which means that I am supposed to design a high pass filter. Okay, high pass filter, and cutoff frequency is 3 radians per second. Okay, 3 radian per second from a LPF having h of s. They, in this problem they already given me the low pass filters characteristic equation, that is s square plus s plus 1 of this format. Okay, they have already given me the h of s. uh, this is from low pass filter. I have a low pass filter characteristic equation. Now I am supposed to compute a cutoff frequency of this and determine the new transfer function. Now new transfer function is this cutoff frequency, that is omega c, or you consider cutoff frequency or pass band frequency, everything will be same. So here, so this is h of omega. Now this is in terms of dB. Okay. Now here what they're trying to say is I need to determine new transfer function with omega c, which means that I need to determine what is h of s for this cutoff frequency of one point. The another point uh, is I am supposed to find out cutoff frequency of low pass filter. So two important concepts here. Uh, so now uh, all the time, as we know that whenever I design a low pass filter, so this is my low pass filter and this will be at minus 3 dB here, right? So this is at, because uh, cutoff frequency, as I told you, h of hb of omega will be equal to minus 3 dB when it is when frequency response is exactly equal to cutoff frequency, right? So this is, now I need to obtain my cutoff frequency here, right? From a given h of s, I don't know what is the cutoff frequency here of what, old, let me take old. So I don't know cutoff frequency of this unless I know the value of this. I cannot transfer this low pass function to high pass function. It is not possible unless I know the omega old, right? Omega old means omega cutoff frequency of my low pass filter, right? So in this regard I should obtain omega c of low pass filter first. I should obtain this. So first obtain this, from that I can transfer. Because if I want to transfer, now go back to the table and observe carefully. uh, yeah, if I want to change this omega p into omega nu, so I need old cutoff frequency, then I already have this, right? So let me write this. So here h of if I want to replace this, so thus s is to be replaced by omega p into omega p of mu divided by s. This is the format. So I have this is 3 radians per second. What about this? I don't know. That is to be fine. So that's what they asked. Compute the cutoff frequency of LPF, then determine the new transfer function, right? So this is all the time it is at the cutoff frequency is always at equal to minus 3 dB. So therefore what we do is, so put s equal to j omega here. So therefore uh, put s equal to j omega, because s is a analog domain and Laplace transform. So this, if I want to obtain the frequency, how do you write? S is nothing but what? Frequency component, right? So my frequency component will be embedded within this S. So how do you write that? So S is nothing but j omega. Now this omega is my cutoff frequency. I have a frequency component omega within this S, within this variable s. How it is embedded? It is embedded in the fashion of j omega, right? So that's why we replace in the Laplace transform, we replace s equal to j omega whenever I want to find out the frequency of that particular transfer characteristic. So now what I do, I from this equation I am supposed to fetch the frequency value. So therefore what I do, I just replace 1 divided by, so s is replaced by j omega, so j omega whole square plus j omega plus 1. So this is equal to what? This is equal to the magnitude of h omega in terms of dB, right? Where do you get this cutoff frequency equal to the frequency equal to cutoff frequency? This is exactly at 3 dB, right? So therefore I write this at 3 dB. It is equal to 3. Now you solve this equation. Now what is to be solved? So this is what? Omega c. This is what? Omega c. Now what is to be find? Solve this equation, solve this characteristic equation. Now in the denominator it is a simple quadratic equation. Solve this and obtain omega c. Okay, now I should able to find this. Now let me solve this. 1 divided by, sorry, this is I think one small mistake I made here. See here, one small mistake. uh, this is exactly same, but what we should do is 20 log of 10 of h of j omega, that is equal to minus 3 dB. This is my standard frequency response curve, right? This is my standard frequency response curve, right? This is my standard response curve. So what is this h of j omega? So that is 20 log of 10. So I got this by applying 1 divided by 1 plus s square plus s plus 1, that is equal to minus 3, right? So this is supposed to be a standard form. Okay, so because this is always in terms of log magnitude, so therefore I should able to write this in the form of, how do you write this in the form of equation? That is 20 log 10 of h of j omega will be equal to, from cutoff attenuation, that is at minus 3 dB. So that is the way how we write, right? So that is 20 log of 10. Now I put s equal to j omega here in this case to fetch the frequency component that is present in my equation. So j omega whole square plus j omega plus 1 is equal to minus 3. Solve for this, solve for quadratic equation, that's it. Solve for quadratic equation. Solve this. Now how do you solve this? 20 log 10 1 divided by, so this is j square. J square is nothing but minus 1 or minus omega c square. Let me write this as omega c, omega c square plus j omega c plus 1. So that is equal to minus 3 dB. Is it not? So uh, now this is a complex form, right? I can write this in the form of, see here, this is, look at this, only you take this part, this part, minus omega c square plus, it is looking like j omega c. Now can I consider this as, so, uh, okay, let me take a real part and imaginary part in this. So 20 log of, observe carefully, I take real part, 1 minus omega c whole square I write. 1 minus omega c square, omega square, 1 minus omega square, omega c square, this is a real term, plus j times omega c is it equal to minus 3. Now look at this, 1 minus j omega square plus j times omega c. Is it not in the form of a plus j times b or a plus ib? Right? Now, how do you solve this? Unless you take a magnitude, it is not possible, right? There is a j term. So what we do while solving, we always take a magnitude like a square plus b square, right? So let me write this. I need only a magnitude of this, right? So I rewrite that equation, 20 log of 1 divided by 20 divided by 1 divided by, so here it is a square. A square means 1 minus omega c. So this is a square plus b square under the square root. I can write it in the form of magnitude. A is nothing but 1 minus omega c whole square. So that is 1 minus omega c square whole square. This is a, plus b square. So that is omega c square. Simple. So that is equal to minus 3. You got this, guys? Simple mathematics, simple trigonometry I applied here. So in this case, I took a real term at one side and imaginary term at another side. So this is in the form of a plus jb. So if I want to have a magnitude, so this is how you try to obtain its magnitude, square root of a square plus b square. So here a equal to 1 minus c square. So a square means 1 minus c square whole square plus omega c square. So that's what here we did. Now you just take this term. So again it is a quadratic equation. Just go ahead with simplification. Go for the simplification process. So this is 1 minus omega c square whole square plus omega c square. Only take this much and try to simplify this. You will going to get in the form of so this is under the square root, right? This is under the square root I should take. So this is under the square root of, okay. Now if I take this under the square root, now solve this current with, thank you. So this from here to here we are going to get 20 log of 1 minus 20 log of under the square root omega c whole to the power of 4 minus omega c square plus 1, that is equal to minus 3. So again omega under the square root can be written in the form of omega c whole to the power of 4 minus omega c square plus 1 whole to the power of 1 by 2, and if I take it on here, so the log factor, because of log factor I can write it as 1 by 2, 20 into 1 by 2 times of log omega c power 4 minus omega c square plus 1, right? So this comes to be 10. So therefore I take it as minus 10 log of omega c to the power of 4 minus omega square plus 1 is equal to minus 3. So this is the equation. Now I can take this to the, this is log 10. So if I want to remove log, then I should go for taking anti-log on both sides. So how it looks? So this is log 10 omega c to the power of 4 minus omega c square plus, so this is 3 by 10, so comes to be, so 3 divided by 10. Okay, so now this is omega c to the power of 4 omega c square plus 1 is equal to 10 to the power of 3 by 10. So this is how you're going to get, right? Solve this. Now you got a simple quadratic equation. Take omega c square as a common factor out of these two, so you can solve it. Okay, let me put one more slide here. So what was the previous line? Okay, omega c to the power of 4 minus omega c to the power of 4 minus omega c square plus 1 is equal to, so 10 to the power of 3 by 10. So this will solve this and let me know the answer. Probably I have the answer directly, right? You can check it. This is 1.995. Just go with the help of calculator, you can solve that. Now what I do is I simply take out this omega c square as a common factor. So if I take it omega c square as a common factor, then I left with omega c square minus 1. I take it minus here, so this is also integer, this is also integer. What I get is, so 1 minus 1.995 minus 1, so that will be 0.995, right? 0.995. In the left hand side I will be having omega c to the power of 4 and minus omega c square. So if I take omega c square as a common factor, then this is how it looks. Therefore omega c square is equal to 0.995, or omega c square minus 1 is equal to 0.995. So what is omega c equal to? Taking square root of this one, 0.995, so that comes to be around 0.998 is the answer. So or cutoff frequency is equal to 1.995, square root of 1.995, that comes to be around 1.412 radian per second. So radian per second. Okay, so the cutoff frequency, so this is what is this value? So this value was, I had a lower frequency LPF which was having omega c. I was not knowing. Instead, they have given me directly h of s, stating that this is 1 s square plus s plus 1. Within this, the value was embedded within this. So what we did, we obtained this value is supposed to be 1.412 radian per second, or it is might be at 0.998. So what we do is, we always take a higher passband value. Out of these two we go for maximum value, so hence we consider this, and assuming we got to know that the older value of omega of low pass filter cutoff frequency was this, Now I should convert this. The second step is convert this to high pass filter. Convert this to high pass filter, and the cutoff frequency, new cutoff frequency, what they told, this is supposed to be 3 radian per second. Now what you are supposed to do? I have h of s current right now. Am I in Google Meet? So I have h of s equal to 1 by s square plus s plus 1. This is a given problem statement. So now convert this h of s transfer function. This is for low pass, that is given in my problem statement. Now convert this to h of s to the HP of h of s, right? So how do we do it? Now replace from the table. I take a replacement, that is from replace my s to omega c old into omega c new divided by s. Okay, this is as simple as that. Now old value s is to be replaced with, older value was 1.412 into the new value is 3 radian per second divided by s. So multiply these two value, so we will going to get 4.236 divided by s. So now in h of s I just replace by, so 1 divided by s square, so that is 4.236 divided by s whole square plus s, so that is 4.236 by s plus 1. Simplify this. Okay, simplify this. Try to write it in the form of numerator to the denominator. Take LCM and simplify this. So we will going to get, I write a final transfer function here. Later on you can simplify and cross verify. S square divided by s square plus 4.236 s plus 17.94. Okay, so this is a new transfer function for high pass filter, which is obtained from, which is obtained from what? From low pass filter. Okay, we designed a low pass filter for some cutoff frequency, and the cutoff frequency was not given in your problem statement directly. So what we did, we derived a cutoff frequency. We solved the equation for cutoff frequency. First, we obtained the old value of cutoff frequency. What was the cutoff frequency for low pass filter? ಅದಕ್ಕೆ ಲೋ ಪಾಸ್ ಫಿಲ್ಟರ್ ಕಟ್ ಫ್ರೀಕ್ವೆನ್ಸಿ ಎಷ್ಟಿತ್ತು, then only it is possible for me to convert that into a new low pass filter with some cutoff frequency that is given. In this case, omega is equal to 3 radian per second. So we know that. How do we write the equation all the time? So for any filter design, if this is my frequency response, how do we write this? This is always like 20 log of h of j omega is equal to -3. This is the standard format that we follow. And h of j omega or h of s, both are same, right? And h of s is given. What is that h of s? H of s is log of 1 by s square plus s plus 1. This is given by the problem statement. So now I need cutoff frequency. Where is my cutoff frequency? Omega. Omega is present within the s equal to j omega. Put s equal to j omega, solve for omega. You will going to get a cutoff frequency of my low pass filter. Use that cutoff frequency and to find out new transfer function for high pass filter. So now you got the high pass filter. Now if you want to see, now you solve this quadratic equation again, you will going to get roots. Two roots you will going to get, right? Two roots are nothing but what? Two poles, right? So we will going to get two poles, and again the poles may be somewhere in the s plane, somewhere else in the left hand side. It has to lie on the left hand side because the reason is stability. Okay, that's it. So this completes your unit 2, the topic called design of analog IIR filter. Okay, so for your internals, so let me stop the recording. So if you have any doubts, you can feel free to ask me. Okay, this video will be shortly, I will put it in YouTube. Okay, thank you. I will come back to Google Meet now.